Today, we're going to continue working on solving oblique triangles. Remember, we have three tools in our disposal to solve an oblique triangle. That's a non-right triangle. We have the sum of the angles in any triangle is 180 degrees. We've got the law of cosines, our generalized Pythagorean theorem. And we've got the law of sines, which says that the ratio of the sine of an angle to the side opposite that angle is constant in any triangle. And we summarize those three equations in this one triple equation. Rather than try to teach you to identify case and associate case with law, I just wanted to say that the way to decide which law to use first is whichever law you can use first. So here's some given information. A is going to be 15, B is 21, and gamma is 73 degrees. Take a moment and decide which case, which law is the only one that we could put this information into. Go ahead and pause the video. And when you come back, we'll talk about the answer. Welcome back. So we got to answer the question, what can we plug this into? I've got A, I've got B, and I've got gamma. Where can I put this information? What choice do I have? Can I put it into the law of sines? If by your silence you mean no, then you're correct. The law of sines requires an angle and the side opposite that angle. We don't have that information. I don't have A, and for A, I need alpha. For B, I would need beta. For gamma, I would need C. We can't use the law of sines. There's no point in identifying that this is side angle side case. We can't use the law of sines because we don't have that information. So that's what we want to notice. Law of sines is not available. We don't have what I usually refer to as opposing information. I don't know why I started calling it opposing info, but that's what I started calling it. I have A, but not alpha. I have B, but not beta. I have gamma, but not C. Those are all pairs that we would be required to use the law of sines. So A without alpha. I have B, but not beta. I have C, or gamma, but not C. The law of sines requires opposing information, A and alpha, B and beta, C and gamma. Don't have that. Law of cosines is the only one that we have available. There's a law of cosines that involves the angle gamma, so that's the one that we're going to use. So we're going to use the law of cosines, specifically the one with gamma in it. And I'm going to use that to solve for C. So that first line of the law of cosines says that C squared is equal to A squared plus B squared minus 2 times A times B times the cosine of gamma. Then we're going to grab our calculating machine, because this looks like a job for calculator. So notice that the only thing that's going on with C is being squared. So to solve, I'm going to want the square root but I don't want to write it all out again. All right, so I have the square root of 15 squared. The calculator doesn't know a difference between 15.0 and 15. So we're not going to worry about that. We got 15, that's given information. Don't have to worry about rounding and stuff. Plus 21 squared minus 2 times 15 times 21 times the cosine of 73. Make sure I'm in degrees. Close the cosine, close the square root, and hit enter. So apparently C is 21.95. We'll call it 22.0. Yes, it did. Because when I hit the square root button, it opens up parentheses. So you got to make sure to keep track of any parentheses that the calculator opens up. So once I hit the square root symbol, since I can't write the line that goes all the way across, I have to put it in parentheses. So when you hit the square root symbol, it opens up parentheses. And so you just start typing 15 squared. What all the other stuff? 21 squared minus 2 times 15 times 21 times the cosine of. Now notice when I hit cosine, cosine opens up parentheses. You just got to make sure that you tell your calculator to close parentheses. So the 73, we need to close the parentheses for the cosine and then close the parentheses for the square root before we hit enter. Both of those parentheses are at the end. If we forget, the calculator can deal. But we don't want to build bad habits now, because sometimes closing those parentheses is going to matter. Sometimes the calculator will get confused if we don't close the right parentheses. So we should learn when parentheses get closed. I have a theory which would be too expensive to test, that if we, instead of using superscripts and stuff like that for exponents, if we just had required everybody to use single line syntax, we might get better at parentheses and order of operations and therefore better at the rest of the math stuff. But yes. If I had forgotten to do that, if I had forgotten to start writing a square root, I would just have done this. So if I had written the 15 squared plus 21 squared minus 2 times 15 times 21 times the cosine of 73. If I had forgotten to do that, I would just say, oh yeah, square root. That way I don't have to draw the line all the way across. If you want to be even cooler, you'll make sure to close the cosine, close the whole string, and raise it to the 1/2 power. That's Winnie the Pooh in a tuxedo. So our decision about which law to use was not up to us. The given information said you can only use the law of cosines. Once we have a fourth piece of information, we can switch to the law of sines. Because if we have 4 pieces of information, we definitely have some opposite information. So now I've got C and gamma, so now we can use the law of sines. Now we can use the law of sines because we have C and gamma. Any questions? So I can use the law of sines now to find angle alpha or angle beta. So now we're going to find our fifth piece of information. And the only option that we have is, or our best option is going to be the law of sines because I've got gamma and C. So I could say that the sine of 73 degrees over C, I want to remember that, oops, that's rounded, is equal to the sine of alpha over A. So I can use this to solve for alpha. I'm going to make sure that I remember that 22.0 has been rounded. So I'm going to use the whole number, not the whole number, that whole thing from our calculator, 21.95007576. It's the most recent number we have, so we have a button for it. So the sine of, so this says that the sine of alpha is 15 times the sine of 73 divided by 22. I want the sine of this number, or sorry, the sine inverse of this value. I'm looking for an angle. Looking for angles means using inverse trig functions. So the sine of alpha is 15 sine 73 divided by 22. Just thinking in terms of proportions. Multiply both sides by 15. But then we also have to find the angle. So we're going to do a sine inverse. So I could say alpha is sine inverse of 15 sine 73 divided by 22. So I'm going to second sine inverse 15 times the sine of 73. Now it's really important that we close the sine parentheses because we're taking the sine of 73 degrees, not anything else. So I close that off from our division operation. Oops. And since I don't want 22.0, I want 21.95007576 plus whatever comes after that. So I'm just going to put second answer, and then I'm going to close my sine inverse command. So this 22 was the answer from before. And I'm just going to use answer because C is rounded. I'm going to use the 21.95007576 number button on my calculator. If I just did sine inverse of 15 times the sine of 73 divided by 22, then I'm going to be a little bit off. I'm going to be at 40.7 degrees instead of 40.8 degrees. If I had said round to the nearest degree, then it wouldn't have mattered. But if I had said round to the nearest 10, the previous one you listed as 40.8, and this one you would list it as 40.7. we're going to use practically the same ratio for finding, oh wait, no, we're not. At this point, I've got angle gamma and angle alpha. As soon as we have two of the angles, we should just subtract to find the third angle. We could use this law of sines to find our last angle. But as soon as we have two angles, subtract to find the third. So alpha, oh, we solved for alpha. Beta is 180 minus the 73 minus 40.8. As soon as you have two angles, subtract to find your third angle. That's a rule that we had in play when we first started solving multiplying. Any questions? How's everybody, okay? Everybody looks stunned. You look like this. Like some monk came through here with a lot of key points. He's like, stunning stuff, stunning stuff, stunning stuff, stunning. You don't blame the monks for this, because D&D monks may be one-trick ponies, but it's a real good trick. No offense if your main characters are monks. Any questions? You can tell that my name is a wizard because I look down my nose at everybody else. I'm just kidding. I'm just saying, stereotypical wizard. Incidentally, when you have a high-level wizard in the party and they're like, oh, well, we could solve that problem. The question is always going to be, yeah, but can we solve it today? Or are you going to have to go study your spell book after a long rest and solve the problem tomorrow? You know what I mean? If you play a wizard, you know what I mean. Or if you're in a party with a wizard. It's like, oh man, if only it was tomorrow, I could prepare a spell that would solve this problem immediately. At which point you're like, oh, I don't think the bandits are going to win. Probably not, because I don't know how many people here actually play music. You should just be happy that your wizard has a better survivability rate. So, than like second edition wizards. I have a theory that wizards actually exist in the real world, but they're so fragile that they just never get to a level where they can really cast spells. And they remain fragile. And this is because I think we're living in a first edition rule set. That's my theory. All right. Remember, the first rule of tangents while teaching is you follow that tangent. You start off, there's a few people that know what the heck they're talking about, but you keep following it until no one knows what you're talking about. Just keep on going. Later on, when you're all in calculus, it'll make sense. You keep following the tangent until the tangent doesn't make sense anymore. So tangent is just an approximation of a function near a point. But it only works if you're really close to the point. The further you move away, you can't just follow straight lines. That's why it's tangent, right? Like if you have a curve, if like a curve curves around like this, curve, curve, curve. The tangent at a point is really close. But the further from that point you get, the less the tangent has to do with what the F you're talking about. So the reason I bring this up, even though we don't do tangents in this class, tangents as a function, but not like tangent lines. The reason I don't bring it up, or that I bring it up now, even though that's more of a calculus thing, is that most people talk about going off on a tangent, but they don't really know what it means. It means at one point, you're at the same place and going in the same direction, but you just kept going in that direction and the curve has moved on. Like, oh, dude, I'm not doing that anymore. So that's why we call it going off on a tangent. It's not a tangent if you just completely change the subject. Then you weren't going in the same direction. You were just going, nope, let's go this way. That's not a tangent. That's just trying to change the subject. That's a non sequitur. We don't have a trig function for that. Any questions? Incidentally, if the line that you're following not only relies on this one point, but two other points, like previously we had talked about subject A, we just talked about subject B, and you tie those 2 points together and follow that train of thought, that's a secant, not a tangent. You're going off on a secant, not a tangent, because a secant takes 2 points. So if you're referring to something before, and then the current one makes you follow that train of thought, that's going off on a secant. So make sure you get your terminology correct. Any questions? Comment? Always make calculus jokes in trig. The best way to prepare for the next class is to do the next class. Let's take a look at another set of information and see what tools we have available. This one's going to be more challenging because the tools are on a previous page. So take a moment and figure out which tool we can use to start solving this triangle. So in this case, we've got A, B, and C. I've got all three sides. That means I don't have a set of opposite information. For A, I need angle A. For B, I need angle, sorry, for A, I need angle alpha. For B, I need angle beta. For C, I need angle gamma to make the law of sines work, and I don't have that. So once again, law of sines is unavailable. We don't have opposite information. So we're going to have to use the law of cosines. Now I've got A, B, and C, and all three versions of the law of cosines involve A, B, and C. So we could use, we're going to use the law of cosines, but in this case, we could start with any angle. So good news. We did not have a choice as to what law we use. It's got to be law of cosines, but we have a choice as, for which angle we go after first. So good news, we have a choice. Bad news, we've got to make a choice. So we can use the law of cosines to solve for an angle. Let's just write down that first one. C squared is A squared plus B squared minus 2BC times the cosine of gamma. So this would be the line I want to use if we wanted to solve for gamma first. Before we plug numbers into this equation, let's solve for gamma and see if we could see any patterns. So if I want to solve this equation for gamma, gamma is in that last term, our generalizing Pythagorean theorem term. So I'm going to subtract the non-gamma terms. So C squared minus A squared minus B squared is equal to minus 2BC times the cosine of gamma. If we think of the order of operations that have happened to gamma, first gamma gets into the cosine, then we multiply the result by the negative 2BC. So if we're trying to undo that, the first thing we've got to do is divide by negative 2BC. So I'm going to have cosine gamma is C squared minus A squared minus B squared divided by negative 2BC. Then we're going to look at this and say, oh, that looks terrible. Dividing by negative 2BC, ridiculous. Especially when we have pluses and minuses in the numerator. So I'm going to multiply top and bottom by negative 1. I'm going to rewrite my cosine gamma as A squared plus B squared minus C squared. Close the top, divide by, open the bottom, 2BC. Oh, not BC. Why did I think I was going to be solving for alpha first? Halfway through the problem, I decided to try to solve for gamma instead of alpha instead of gamma. Geez, glad that got recorded. So I know I'm writing it on single line syntax, but that's a top and a bottom. The numerator is c squared minus a squared minus b squared. The denominator is minus 2ab. They both need to be in parentheses because they both involve operations. So I don't want to make sure that I have my numerator and my denominator in parentheses. Then the last thing, if I want to know what gamma is just find the cosine inverse of this expression. So the last thing would be to say that gamma is cosine inverse of a squared plus b squared minus c squared. Close the numerator, divide, open the denominator, 2ab. Close the denominator, close the cosine inverse. Any questions? It's like, so the first, the green part, I just divided by the minus 2ab. So another way that this might appear, I have the cosine of gamma is c squared minus a squared minus b squared, and we divided by the minus 2ab. So that's what it looks like in vertical format. I got the numerator and the denominator. Then the next part was my distaste for this negative in the denominator. So what I'm going to do is I'm going to multiply by -1 over -1. When I multiply the denominator by -1, that just becomes positive 2ab. I get a negative c squared plus a squared plus b squared. And I just put the -1 at the end. So a squared plus b squared minus c squared. Now, before we actually use this to solve for gamma, to actually calculate, to calculate gamma, look at the pattern, think about the patterns that we have in the law of cosines and how we can easily adapt this to be the solution for beta or the solution for alpha. If we wanted to write the equation, the law of cosines solved for beta, I'd have a cosine inverse Now, in this case, instead of gamma and C being opposites, beta and B are opposites. So the two positive ones from the numerator will be a squared and c squared, but minus b squared. And instead of 2ab, it'll be 2ac. The negative square and the angle, those are the ones that are opposite. Those are the matching ones. Then it's the other two. So if I wanted to solve this for alpha, we could also write a cosine inverse, and then we would just have to switch some things around. But that's the format that we have. In the context of this problem, I would say that gamma is the cosine inverse of the numerator, a squared plus b squared. So 15 squared plus 21 squared minus c squared minus 30 squared. Close parentheses, divide by open parentheses, 2 times 15 times 21. Close the denominator, close the cosine inverse. Cosine inverse of the numerator, 15 squared plus 21 squared minus 30 squared. Close at the top, divide by open the bottom, 2 times 15 times 21. Close the denominator, close the cosine inverse, hit enter, 111 degrees. Any questions? How's everybody okay? At this point, we've got a set of opposing information. I've got C and gamma, so I could start using the law of sines. Still only got one angle, but I could use the law of sines to find another angle, or I could use the law of cosines to find the other angles. I can just go all in on cosines. And law of sines can go away for this problem. This is one of the things that makes this difficult. The decision that we have to make, the choice is almost always made for us at the given information stage. We've only got 3 pieces of information. That will determine what law we use first. Once we have a 4th piece of information, we could just switch to the law of sines because it's easier. Or if we happen to remember this pattern, if you happen to be wired to remember these patterns, and you can easily translate, easily permute the A, B, and C to solve for beta and then to solve for alpha, that might be faster. I can't tell because I'm not allowed to read your minds to see how they work. I'm not allowed to run psychic diagnostics on how your minds work to see which one would be the best choice for you. That means you have to decide which is going to be best. Do you want to, in this situation, use the law of cosines in its other 2 forms and find alpha and beta, or you want to switch to the law of sines because we now have 4 pieces of information, which guarantees we can start using the law of sines. The only way to find out is to do both. I know that this is really counter to the student plan for doing things. I'm not going to do a problem twice when I can do the problem once. Comment? Now, before you say, I'm not going to do the problem twice because I'm opposed to extra work, that is incorrect. Y'all are definitely not opposed to extra work. You know how I can tell? Y'all are here. This is optional school. Extra work. Extra work that you ain't getting paid for. That's crazy. At this point, I'm not going to take a job for $0. Worse, $-. That's insane. Especially if you've got to take classes from me. Holy crap. Y'all got screwed in that deal. Questions? Comments? Deep thoughts? Snide remarks? All right. What's next is we got to look at the different cases for using the law of sines, because it might be if we have a set of opposite information, if our opening set of information has A and alpha, we're going to have to use the law of sines. So what you want to do is check out the book in 7.1 and 7.2. You can look at the two cases today where we had to open with the law of cosines and figure out what those cases are called. Even though I don't use the cases as a way into which law to use, they are still useful tools. That makes sense? I'm not saying this is one way or the other. More ways are better than one way. How's everybody okay? All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.